Hi everybody, this video is going to go over how to use an orbital diagram to write electron configurations. When we go through using this orbital diagram, we will review the 3 rules on how electrons fill into orbitals. I'll explain why we see some of these orbitals come in a funny order that might not be expected. And then we'll do some extra practice at the end. So here's our orbital diagram. I'm going to zoom in a little bit so that we can see the writing a little better as we're taking our notes. All right, so the first rule that we have is called the Aufbau rule. And the Aufbau rule, remember, says that electrons are lazy. They want to fill the lowest orbitals first. They want to use the least amount of energy they can. So we're going to write here, electrons are lazy. They want to use the least amount of energy possible. So what this means for using our orbital diagram is that we're going to fill from the bottom of the chart to the top. It takes less energy to put an electron in the 1s orbital than it does in the 4s. So we're not going to start like way up here. We're going to start at the bottom and go from lowest to highest energy. The next rule that we have is going to be the Pauli exclusion principle. I'm just going to write Pauli for the sake of space on our paper here. And this says that 2 electrons per orbital one is spin up. We'll use a little half arrow going up, and one is spin down. We'll use a little half arrow going down. So what that means for our orbital diagram is that inside each orbital box, we can have maximum 2 electrons. And that's how we would draw them. If you're wondering why we use the little half arrows instead of a full arrow up and down, it's because that fits in our boxes much better. So it's very common to see people use these little half arrows just for the sake of space. So now let's pause there with our 3 rules. We'll get to the third one in a minute. I'm going to scoot up here where I have some extra space. And we are going to be trying to figure out the electron configuration for fluorine. Now, if you look at your periodic table, you'll see that fluorine has 9 electrons. So we're going to be allowed to put 9 arrows in our picture. In this diagram, we'll have to put 9 arrows. So we're going to start at the bottom where we have the lowest energy. I'm going to put 1 spin up. I still have space here, so I'm going to put the next one, but it needs to be spin down. So I just followed Aufbau and I followed the Pauli exclusion principle. So there's electron 1 and 2. Next we'll come up here. Here's electron 3 and 4. And now up here is electron 5. And we're going to pause and take a look at this because this is where our third rule comes into play. If you look right there, all of those 3 orbitals are at the same energy. So that's when we have to think about rule number 3, which is Hund's rule. Remember, Hund's rule is the one that talks about how the electrons don't want to have to share an orbital if they don't have to. Kind of like siblings don't want to have to share a bedroom unless they absolutely have to. If there's space available, they would like to have their own room. The electrons would prefer to spread themselves out. So what we're going to do is we're going to put 1 electron per orbital, and then and only then can they double up. So we had electron 1 and 2, 3 and 4. Here's 5, 6, 7. I spread them out. There was 1 electron in the px, py, and pz orbital. Now I'm going to go back and I'm going to double up because there's still space available at a lower energy level. We don't want to go up to 3s yet because there's still spots here. I've spread the electrons out as much as I could. Now I do have to go back and double up. So we had 1, 2, 3, 4, 5, 6, 7, 8, 9. Now sometimes at this point people look at this and they think, oh no, something's wrong. This box is not full. That's fine. It does not have to be full. It can be empty, it could be half full, or it could be totally full. What matters is that you use the correct number of electrons. Fluorine only has 9 electrons, so I better only have 9 electrons here. When you have an empty box like that, we call that an unpaired electron. And for the most part, atoms don't like that. It doesn't feel very stable to them. So fluorine really likes to come through and steal an electron from another atom to try to fill this empty spot. So if fluorine had its way, it would become a -1 ion because it would like to come and steal something electron from something else to fill this gap. Okay. All right, now to write the configuration, we're going to list the energy levels and the orbitals that we used in order. So we started with 1s, and the 1s orbital has 2 electrons. The 2s had 2 electrons. And careful here, the 2p orbitals had 1, 2, 3, 4, 5 electrons. We want to make sure that we don't go on autopilot and just write what it would be when it's full, because it may not be full. All right. Next thing I want to show you is kind of the order that we would fill things in as we went further up the chart, because it gets a little bit complicated. We don't always go in numerical order. The d electrons and the f electrons, the d and f orbitals are such strange shapes, they take a little bit more energy to put electrons into. So sometimes the electrons will try to skip them, and they'll try to wait as long as possible before they put electrons into those weird orbitals. The analogy I like is maybe you have a class where you don't really like having to do the homework. You know you're going to have to do it eventually, but you keep procrastinating and you put it off and you put it off until you don't have a choice and you really have to do the homework. Hopefully that's not chemistry class for you. For me, that was always my English class, right? I never wanted to do my English homework. I'd always leave it until the last minute I could. And so filling the d and f orbitals are kind of the same idea. They're going to have to get filled, but sometimes they get filled in a weird order because the atom is procrastinating. So we're going to go from 1s to 2s, just like we did. we go from 2s to 2p. Once 2p is full, we go to 3s. So far, pretty straightforward. 3s to 3p. If you keep having enough electrons, you just keep going. You go 3p to 4s, and this is where things get strange. If you look here, we didn't go from 3p to 3d because the 4s orbital is a little bit lower in energy. We're going to procrastinate, and we're going to try to wait to fill these until we have to. So the lower energy is 4s. So now that that's going to be full, then you would have to go to 3D. Then you go to 4P. Then you go to 5S. And if you look here, 5S is at lower energy than 4D. So we filled that one first. Then we go to 4D. Then we go to 5P. Then we go to 6s, and if you look, we waited all the way until here to finally, for the very first time, fill an f orbital. So we went all the way to 6s and then 4f. We really procrastinated filling those f orbitals. After 4f is 5d, 6p, 7s. From 7s, then we go to 5f. Once 5f is full, then we do 6d, and then at the very end, we would do 7p. And as of now, that's where we stop. Who knows, maybe in a few years, they add some new things that they've discovered, and we add some extra orbitals, but for now, that would be the end. So let's kind of run through it. Instead of just going 1, 2, 3, 4, 5, 6, 7 in order, we will have to jump around. So 1s, 2s, 2p, 3s, 3p, 4s, then the 3ds, 4p, 5s, 4d, 5p, 6s, finally 4f, 5d, 6p, 7s, 5f, 6d, and 7p. Now, usually at this point, people start worrying that they're going to have to memorize the order that this goes in. And the answer to that is yes and no. You will not have an orbital diagram on quizzes and tests, but you will have a periodic table. And the next video will show you how to use a periodic table as a shortcut cheat sheet for an orbital diagram. Believe it or not, the periodic table is set up in a funny way, in a funny shape, that matches the exact orders that we see here on our orbital diagram. So even though you won't have this document, because you get a periodic table, pretty soon you'll be able to see the same pattern just by looking at your periodic table. Okay? So the last thing to add to this note sheet is a little reminder that we have to be careful with our Aufbau principle. Okay? So I'm going to write careful rule number 1 of Aufbau. We're going to have to zigzag up the chart. Right? That's our reminder that you have to go in a funny order so that you are always following Aufbau from lowest energy to the highest. Sometimes people will say, well, if 4F is way up here, why is it still energy level 4? And that's because it really has to do with the distance from the nucleus, not the energy that it takes to fill that electron. So remember that the number in front here is really more referring to the energy levels in terms of distance from the nucleus. Okay? All right. Next, you should have a sheet of practice problems. Zoom out a little bit. I'm going to do the first couple of these with you under the camera. Then I'm going to have you pause the video. I'm going to have you try the rest of them. And then you unpause the video and you will see all of the answers. Now for now, we'll be using an orbital diagram. And if we had to print a different orbital diagram for every practice problem, we would use so much paper. So what I like to do is I like to print an orbital diagram and put it inside one of these plastic sheet protectors, right? Then I can use a whiteboard marker and I can write on it and then erase it, and then write on it and erase it, okay? So you can try that if that's helpful. Okay. All right, so first thing we need to know is how many electrons each of these have. Remember, we're going to look at the periodic table to find the number of electrons. If we look at the periodic table, we found phosphorus, for example. Up at the top, it would have a 15. That's our atomic number, which is the number of protons. If it were an ion, we would have to adjust, but we're not doing ions right now. We're just doing normal elements, neutral. Okay, so phosphorus has 15, sulfur has 16, bromine has 35, neon has 10, lithium has 3. Why don't you go ahead and pause this video? You try to fill out the rest. I'll fill them out, and when you're ready, unpause the video and you can check your answers. All right, hopefully you actually paused the video and gave it a try. Check your answers. These are the number of electrons that we'll be using. So now I'm going to switch to my orbital diagram and my whiteboard marker. We're going to do phosphorus first. Phosphorus has 15 electrons. I'm going to start at the bottom. 1, 2, 3, 4. Now I have Hund's rule. 5, 6, 7, 8, 9, 10, 11, 12. Hund's rule again. 13, 14, 15. So phosphorus, if we look, has 3 unpaired electrons. So phosphorus actually likes to go steal 3 electrons from other atoms, trying to fill these empty spaces. It's easier for phosphorus to go steal 3 more electrons than it would be to get rid of all 5 of these energy level 3 electrons. It would be a lot less work to gain 3 than it is to lose 5 of something. So that's why phosphorus likes to make a -3 charge. So now, if we're going to write our electron configuration, we're going to list from the bottom to the top, and we're going to list all the electron orbitals that we used. So we have 1s, 2, 2s, 2, 2p6, there were 6 here, 3s2, and we're going to end with 3p3 because there were only 3 electrons here. So on our paper, let's write our final answer on our paper. So we're going to have 1s2, 2s2, 2p6, 3s2, 3p3. Okay, make sure that your superscripts look like superscripts. Make sure your big numbers in front for the energy levels look like big numbers. Make sure you're using lowercase letters for our orbitals. And you don't need to put commas or anything between these. Just list them in order. Okay? All right, next is sulfur. It has one more electron. So I'm going to be lazy and I'm just going to do this. I'm going to change this to be sulfur with 16 electrons. Look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now I come up and I double up, 16. So sulfur, instead of ending in 3p3, is going to end in 3p4. So come over to your paper, 1s2, 2s2, 2p6, 3s2, 3p4. And if you look, sulfur has 2 unpaired electrons. So it's going to try to go steal 2 electrons from something to fill these spaces. So sulfur likes to make a -2 ion. Okay. All right, next, a huge one, 35 electrons. We're going to do bromine. All right. Alpha says we're going to start at the bottom. Pauli exclusion says we can only put 2 electrons per box, 1 spin up, 1 spin down. Hund's rule says we're going to spread our electrons out when we have the same energy level possible here before we come back and double up. So let's put 35 arrows into our diagram. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, careful, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Now over here, 31, 32, 33, 34, 35. I had to follow Hund's rule several times. I had to do Hund's rule here. I had to do Hund's rule here. I had to do Hund's rule over here. And Hund's rule over here. So I had to do it a lot of times where I had to spread the electrons out before I doubled them up. So now, if I want to write my configuration, it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p. How many do I have? 1, 2, 3, 4, 5. 4p5. Make sure that you do not list them in numerical order. Make sure that you list them in the order that you filled your orbitals. That's why this diagram is helpful. Okay. So let's put that on here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Okay. All right, next is neon. And we're going to see something special happen here on neon. Neon has 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And what you should notice here is that the entire second energy level is full. When the S and P orbitals are full for an energy level, it's extra stable. It's very, very, very stable. We call things that have this full S and P noble gases. So neon is a noble gas. Because those orbitals are full, it does not want to steal electrons, and it does not want to give any of them away. So it is very, very stable. Sometimes you may hear them called inert gases. Inert means they don't like to react with anything. And so you can see if something is a noble gas by looking at the configuration you have here. The atoms don't really care if their d and f orbitals are as full. It's really more about whether this s and p set are full. So that's one way you can look to see if it's a noble gas. Okay, so I want to come and put my final answer on my paper. For neon, it's going to be 1s2, 2s2, 2p6. All right. Why don't you go ahead and pause the video, try the rest of them, give it an actual try, unpause the video, and I'll have the answers under the camera for you to look at. Okay? So go ahead now and pause the video. All right, here are the answers. I know the worksheet looks a little different than what you have, and what I've been using, this answer key is just an old format, but it's the same problems, don't worry. So you can pause the video, take a look at these answers, double check them. If you got one wrong, try using your orbital diagram again. Make sure you follow Hund's rule. Those are usually the places people make mistakes, is they forget to follow Hund's rule, or they forget to zigzag up the chart, and they forget to be a little bit careful with Aufbau's rule. That's usually where our mistakes are. Okay? All right, I hope that was helpful. I know that was a little bit longer than most of the videos, but hopefully the practice problem portion was helpful as well. All right, everybody, bye.